So in our last little section here, we're trying to apply what we looked at in the last section by analysing whether reaction is feasible or not feasible based on the values of delta H and delta S. We're doing a slightly different calculation here. We're actually trying to calculate the specific temperature at which a reaction either becomes feasible or not feasible. In other words, the tipping point between feasible and not feasible. So the tipping point for a reaction, that difference between feasible and not feasible, is always going to be when delta G equals 0, because obviously when delta G is positive, it's not feasible. When delta G is negative, it is feasible. So the difference, the kind of interchange between those two terms is going to be delta G being 0. If delta G is any higher, then it's not feasible, and lower, reaction becomes feasible. Therefore, if we calculate the temperature for which delta G equals 0 exactly, we find the temperature at which the reaction starts or stops becoming feasible. In terms of how we do that, it involves a little bit of clever manipulation of the free energy equation. Because we've got the delta G equals delta H minus T delta S, we're now trying to find the values for which delta G is exactly 0. So we sub that in the next line. That means we can bring our T delta S term over the other side. So we get T delta S equals delta H. And we want to find the temperature for that delta G being 0. So we need temperature by itself. So we bring delta S over the other side and we get T equals delta H divided by delta S. So in other words, for a reaction, if we divide delta H by delta S, we will find the temperature at which it starts or stops becoming feasible, the kind of tipping point between those two scenarios. So let's just have a wee go at that. So first question, determine the temperature at which the following reaction becomes feasible. So we're given a delta H, given a delta S. So I'm just going to use T equals delta H over delta S. Now one thing I'd be careful about again is making sure my units are consistent. So delta H is given as plus 312 kilojoules per mole. However, delta S is given as 489 joules per Kelvin per mole. I have to make those energy values be the same. So the standard way of doing that is dividing the entropy by 1000. So it's going to be 489 over by 1000. You can just do that in your calculator in one step, putting it on the bottom of the fraction. Type it in and that gets a value of 638. Remember that is in Kelvin because that's the unit of temperature in the units here. So what we're saying is that the following reaction becomes feasible at 638. You might be a bit confused by what we're saying here. Is it saying that above that or below that we get a feasible reaction? Again, if you think about it, the delta H and the delta S are both positive here. So what we said before is, on the previous page, if they're both positive, it becomes feasible above a certain temperature. So what we're really saying is this reaction becomes feasible when you get higher than 638. But the tipping point, the important temperature is at 638 there. Question 2, below which temperature will the following reaction become feasible? So again, we just got two values, so we just plug them in. T equals delta H minus, or divided by delta S. Delta H is minus 795. Delta S is minus 152, have to divide by 1000. And that gets me 5230, which is a very, very high temperature. What we're saying is below that really high temperature, the reaction is going to become feasible. Again, that's because the delta H is negative and delta S is negative, so it becomes feasible below a certain temperature. Because the temperature is so high, what they're basically saying is it's basically always feasible. It has to be getting really, really hot for it to not become feasible. But again, below that high temperature, it will become a feasible reaction. And our final little section on page 16 is the same kind of mathematics, just applied slightly differently. We're looking at physical changes here. So in the last page, we're looking at the temperature for which a chemical reaction becomes feasible or not feasible. Here we're looking at physical changes, so no chemistry, just actually physical changes of state. So during the change of state, the system's at equilibrium. So that kind of means you're not really sure whether it's a solid, liquid or gas, depending on what temperature you're at. If you think about water at 0 degrees C, whether it's melting or freezing depends on the direction you're going. If you're cooling it down, it's freezing. If you're heating it up, it's melting. At exactly 0 degrees C, you can't really say whether it's melting or freezing. What we mean by that is it's actually at equilibrium. It's either going forward or backwards between solid or liquid. Because it's at equilibrium, we generally would associate that with being delta G equals 0, because it kind of at that tipping point between two sides of a physical change. So if you take into account that during a physical change, at the melting point or boiling point, your delta G equals 0, it's possible for you to work out enthalpy changes or entropy changes associated with state changes. You might not follow that fully, but it'll be easier looking at this example here. So it says the standard enthalpy values of bromine as a liquid and a gas are 152 and 245. The boiling point in bromine is 332 Kelvin. Determine the enthalpy change of vaporization for bromine. So we're looking for this physical change here, basically boiling bromine. So Br2 as a liquid going to Br2 as a gas. And we want to find the enthalpy change for that process. So the fact we need to use is, for a physical change of state, we're saying that delta G equals 0. So that means I can calculate the temperature by using the same equation on the last page. T equals delta H over delta S. Now, a little bit more work on this question. I'm trying to find delta H here. So delta H equals T delta S. I've got the temperature, it's 332. I need to calculate delta S though, because I've got the entropy at the start and the end. So delta S is just going to be the entropy for the gas, which is 245, minus the entropy of the liquid, which is 152, which equals plus 93. So that's the entropy change when you change it into a gas. Putting that into my equation, I'm just going to get temperature is 332 times by 93 over 1000, have to make the units consistent. And that gives me a final value of delta H for that physical change of state of being plus 30.9 kilojoules per mole to 3 significant figures. So if you get a question about a change of state and calculating an entropy or enthalpy change for it, key fact to remember is that delta G is 0 for a change of state.